Velhal Shridhar. His work was on development of spatio-temporal task assignment for perimeter defense problem. Shridhar, go ahead and present.
Good afternoon, all. Today I'm giving a PhD defense on the topic of development of spatio-temporal multitask assignment approaches for perimeter defense problem. First, I'll start with what is the perimeter defense problem?
Hello, Professor Suresh. I can't see the slides.
Just one.
Mangal, can you see? Can you see now?
No.
Okay, I'll just reshare again.
1 second.
Or others can see. Anyone other can confirm.
The entire screen.
Yes. Now I can see desktop.
Can you see now?
Yeah.
Putting it full screen, can you see now?
Yes.
Nice. Thank you. Good afternoon. Today I'm presenting a defense spatio-temporal multitask assignment approaches for perimeter defense problem. So first, what is perimeter defense problem? Let us consider there is one territory which we want to protect. Consider building of IISc which we want to protect, and there are some intruders denoted in the red color. UAVs, they want to penetrate it, and we have some defenders which are restricted to operate inside the boundary or on the boundary, and they will try to protect. And we need to find a strategy for a team of defenders so that it can capture or neutralize every intruder on the boundary. And for that purpose, we are also using the concept of reserve stations, which are kept inside. So in general, the problem is what is the strategy of defenders? So the organization of the presentation, first I'll motivate the problem, why this problem is important. Then I'll go through the literature review on the pursuit evasion games, guarding games, perimeter defense. I'll point out the research gaps. Then I'll formally formulate the problem and define the objectives. And then I'll propose the solutions in 4 steps. First, problem is spatio-temporal multitask assignment approach. Then the dynamic resource allocation algorithm. Then priority-based algorithm. Then decentralized approach and the application. And finally, I'll conclude and comment on the future directions. So first, I'll point out the contributions of this work. In this work, I'm proposing the dynamic resource allocation allocation for using multitask assignment approach, and this we are using the spatio-temporal multitask assignment formulation for the problem. This is the first formulation. Then, when your problem is defined in STMTA, we require some minimum number of defenders or agents to execute given task. So, what is the minimum number of agents required? That optimal value is computed, and the solution is obtained in 2 steps. This all is valid when we are assuming that intruder coming in straight line. When intruder is maneuvering, is agile, the prediction of the task changes. Prediction at intruder is coming, it changes. For this purpose, we are defining the static design and the sequential capture solution for agile intruders. Next, I will propose the decentralized solution, which uses the distributed computation with the partial observations of the defenders, and solution is scalable. And finally, I'll show it on the application of pickup and just-in-time delivery problem with demonstration. Motivation. So nowadays, UAVs are used in many real-world applications such as logistics, defense, search and response, and many more. But with the free use of the UAVs in free airspace, they pose challenges in privacy, safety, and security. So there are some incidences occurred in Saudi oil refineries or the Heathrow Airport or Jammu Air Base, where drone comes and attacks. The current solutions are majorly based on the no-fly zone or the passive methods such as the sensor jammers and spoofing. So we need to have some active solutions. So for this, we first now define a problem. Let us consider a territory which we want to protect, and we define it using a convex shape region. Then intruders are trying to penetrate. And we need to avoid it by using a team of defenders, which are denoted in green color. Now, how we are doing it is like we are estimating when the intruder is coming on the boundary, defender should reach there at the same location at same time when intruder arrives. This defines a spatio-temporal task, which defines the spatial location at which intruder is coming and the time at which it is coming, and defender needs to execute it. So related works, first this problem has been solved for the guarding problems where the defender is allowed to operate outside the territory and defender will try to capture the intruders outside the territory. This problem has been solved for 1-to-1 and multi 2-to-1 or many-to-1 problems. The next problem is solved as reach and avoid games. This problem plays the multiplayer game between end defenders and attackers. And here, if they cross the boundary and reaches to the yellow region, the intruder gets a point. So whoever gets more point wins the game. So perimeter defense problem is defined by the Aerospace perimeter, and intruders are agile, they are coming out from the outside. Initially, they use the problem of 1-to-1 problem and they compute the feasibility region along the outside the territory, says that in the region which separates out when the intruder is feasible for a defender and when it is not. And based on that, using 1-to-1 assignment, they compute the feasibility sets and then solve the matching algorithm to make assignment for a defender to an intruder. Now I point out the research gaps. The scalability, if number of our earlier work uses the number of defenders are always more than the number of intruders. But what if intruders are more? This is an unknown scenario. We don't know how many intruders are coming. So scalability is a major question. Then the dynamic intruders can come after some time and they can be online coming. Then the distributed sensing and partial observability. Each defender will have some limited sensing range. So it can detect only few intruders. And then defender needs to coordinate with them and share the information to have a group or the team planning. And the sequential capture. As the number of defenders are less than the number of intruders, the defenders needs to plan accordingly and they capture the multiple intruders in a sequence, one after another. So how can we plan this sequence? Yeah. So objective of the problem is to capture the intruders before they enter the territory. So what it demands is we need to stay inside the boundary. And if intruders coming to boundary, we need to capture it on the boundary. Here we are assuming that defenders are equipped with the sensor, homogeneous sensors. They can communicate with each other. Another assumption we are using is number of intruders are more than number of defenders, but the velocity of defender is more. So defenders have a velocity advantage. Here in this work, I'm considering both non-maneuvering and maneuvering. First, I'll consider the non-maneuvering intruders and then maneuvering. And we define the neutralization is whenever the intruder comes in epsilon vicinity of the defender, it gets captured instantaneously. Yeah. So I'll now formally define the problem as spatio-temporal multitask assignment problem. So let us consider a problem, intruder I1. Yeah. So let us consider intruder I1 is predicted to come at location P1T at time T1. So it defines that it is coming at location P1T at time T1. So it generates a task of T, P1T, small t. Similarly, all other intruders will define their own spatio-temporal task and defender needs to execute them. So let us consider the problem in the, we divide this territory boundary in angular positions and show it in between -pi to +pi. So each point on this angular point will represent a unique point on the boundary. So now we show it as if intruder I2 is coming at angle 0 at time equal to 5 seconds. So it defines the task T2 in this spatio-temporal plane. So what it means is the task is available only at this point T2 at specific position angle and specific time. If defender reaches that before time, it has to wait till intruder should come. If it reaches late, then intruder is already penetrated and defense is failed. So now I formally define the cost required for the defenders to capture the intruder. So first we are defining cost for the defender from its own location to the first task is task J. We define it as the distance between the initial location of the defender to the task location. If the available time is less than, if the required time is less than available time to travel. If defender cannot travel that distance, we use the value kappa to avoid those assignments. Naturally, after when defender moves from the k task to the j task, the distance is the relative distance after task k to task j, is pj minus pk, and then we check if it is feasible, is what is the time required is less than time available. We take distance as it is. If time required is actually not sufficient, then we take the value kappa, and if I have to do the task in negative time, means I have to go in previous time, it's infeasible, completely infeasible, so we put the value infinity to avoid those assignment completely. And then we define the multiple TSP problem where we are trying to minimize the distance cost for the first task for all I and all j. So, and then for the cost of the subsequent task for all k and all j. And here the delta IJF denotes this decision variable for first task, which can take value 0 and 1, which says is the defender is either assigned or not. And then a subsequent task delta kj denotes, it also takes value 0 to 1. 0 denotes the task is not assigned, 1 denotes task is assigned. And here we are using three constants. The first constant denotes that each task is executed only once. The second is saying that each defender can almost do one task. And the last constant is like defender can execute at most one task immediately after the previous task. So you can do task in a sequence, but from one location you can go to next. From there you have only one next in a sequence. So now I'm defining the dynamic resource allocation assignment approach. So what is the question? It's like when we define the task, is the given number of defenders are sufficient to execute the given task? What is the guarantee that defenders can do it? So question is if they are sufficiently away, it can do it. But sometimes intruder can be faster. The time available between those two intruders may not be sufficient for a defender to execute that task. So we need to have extra defenders. So let us consider some example. If we are in aerospace department, we have to go to hostel and then to main building. Some time required to go to hostel, but then time from hostel to main building may not be sufficient. If I have to go there within 1 minute, I cannot walk within 1 minute from a hostel to main building. It is a forward in time, but I cannot reach due to my velocity limits. So we need to assign another defender, another agent. One will go to hostel, one will go to main building. So how to calculate those required number of defenders to execute the task? So is simple because we separate the tasks which are forward time infeasible and which are negative in time. So we'll first solve the problem with given assignments as it is. Then we'll compute what are the infeasible assignments from the solution, and then add those many defenders in the team so that the problem becomes feasible and all assignments can be executed. And this is the minimum. We can prove that this is the minimum number of agents required to execute given task. So features of this algorithm, it requires only 2 steps to calculate. First is raw solution with the given defenders, and second, you have to solve the problem with updated team of defenders. The solution is scalable and online computable, and also it is simple. Yeah. So theoretical analysis about this is feasibility due to addition of one defender. So if given a problem, if we add only one extra defender, what it affects? So if we solve the problem and it has q number of the assignments which are forward time infeasible, and if we add only one extra defender, then forward time infeasible assignments will be q minus 1. So only one forward time infeasible assignment becomes feasible. So the corollary says that, okay, if I add q defenders, all tasks become feasible. Yeah, and the next theorem is like collision-free solution. The solution of the dream approach is optimal solution, and if you are calculating using it on the Euclidean plane, all the trajectories obtained will be collision-free. There will not be any conflicts. This is simulation result for dream algorithm, where intruder I is coming to here and the capture. So here the color denotes the sequence and assignments. So red will assign for red. The star denotes the first assignment. Delta denotes the second. And here we can see the defenders are added dynamically and removed dynamically when you are not required. I'll go for me. Yeah. So what are the issues with the dream? So it assumes that my velocity direction by which I predicted the location of the intruder when it comes as it is. What is the issue? If the intruder ij is predicted to come at point P1 due to velocity, but it is very closer to point P2. And if intruder changes its heading direction, the defender may not be able to capture it. So what we propose is like taking some median point where we'll equate these ratios so that the point of the arrival location can be predicted in better way, considering the closest point and the velocity direction. But still it is not suffice. The another issue is the sequential capture. Let us assume we have two I1 and I2 intruders. They plan according to the previous way and we get the unique or the better estimation of the arrival point. Still both of them can deviate. And now the defender D1, which already in the previous step which was able to capture both in sequence, may not be able to do it because both of the intruders are changing their direction in opposite way. So we need to ask for a reserve station. The question is, when should we ask for reserve? It should be feasible for reserve, right? If you are asking some help, the one who is giving the help should be able to do it. It should be in its capacity, right? So we need to address this. And yeah, and what obviously, if we are solving using only dream algorithm, the performance will degrade drastically for agile intruders, and for almost 45° per radian maneuverability of the intruder, it completely fails. That at least one penetration will happen. So next we are proposing the priority based dream algorithm. So issues are here same, right? So what are the observations? Defender can handle a single maneuvering intruder, but not in a subsequent way. So I can handle one-to-one assignment properly. The issue is if both are deviating, I cannot do it. One deviating, it is possible. Approach is we have to prioritize the critical intruders as a first task. So which are sufficiently close to the boundary, we assign them as a priority. So which are sufficiently close, they always handle as a first task. And which are away, they can be taken as a subsequent assignments. So here I'm defining the steps, static design steps. These steps are defined for a single territory. And once territory is given, we can solve this in an offline way. So we'll first calculate the number of user stations required. Then we can compute what is the priority region. It is the region outside the territory where it is critical. Next, we calculate what is the monitoring region from which is sufficient region which I observe so that I can capture all. Then we'll define the number of defenders required on the boundary so that it can sense the entire region. So what is the minimum number of defenders required, active defenders required on the territory so that we can sense all the region? Yeah. So first we'll say how to compute the reserve stations. So it's basically we need to compute the point on the inside the territory so that it will try to minimize the maximum distance to any point on the boundary. So if I need, and then for multiple reserve stations, I need to define it for the best location from the reserve station. If I choose the best reserve station, what is the minimum distance I need to travel? What is the minimum of the maximum distance I need to travel? Next, we define the priority region. So for this purpose, we define the cost as a value function j, which is the time of the intruder required to travel any point P minus the time of best defender can reach there. So it's a T intruder minus best of defender. And if we try to maximize this function over all the points on the boundary, we'll get a value of zeta. And now if zeta is positive, we say that it's infeasible because zeta is positive means intruder can reach earlier than the defender. If zeta is negative, then defender can reach there. So it separates out the problem as which is the feasible region and infeasible region for the reserve stations. And now we define the zeta whenever it is positive as a priority region. Now let's convert it to the from time to velocity and the positions. So we just define the time is converted into distance by velocity of intruder defender. We get the gamma velocity ratio gamma, and we'll define this omega p as the points where the gamma function is positive and the region is outside the region omega, territory omega. So next, we solve this, we can get a priority region, but there can be uncertainty. There will be some issues in the sensing monitoring. So we need to have put some safety factor where we are using the safety factor of beta in the velocity of the intruder. And then we define, okay, this is a region I need to monitor. If I monitor this region, I have some safety about with me. And we will follow the same step to calculate the region omega m, which is the monitoring region, where zeta m is positive. And yeah, zeta m is a function of I, is the intruder location, the gamma is the velocity ratio, and beta is the safety factor. So if you see in this all, the solution is entirely dependent on the intruder position, which is unknown, and the velocity ratios. So if you solve it once offline, there is no need to solve it again online if regions are defined. Yeah. And the last is we need to find out what is, okay, I now define the what is the monitoring region which I should monitor, so that all the guarantees, we can give the guarantee that all intruders can be captured. We solve the problem again with the monitoring region as our boundary, and what is the best location inside the territory where I'll keep, so that minimum distance. So here minimum distance is the minimum sensing range required to observe that or monitor the region. So it's in the same problem, just we are using maximize over the, instead of omega, we are maximizing over the omega m, which is the monitoring region, and we define the critical points on which we are minimizing. And then we calculate what is the minimum radius required, is the maximum of. Yeah. Okay. Now question comes, what are the radius commanded obtained from this solution? Minimum radius, it may not be feasible. The sensors does not have that. So what to do? Like I solved the entire problem, but it started with the assumption that I have some number of the reserve stations. So, and what are the solution obtained for the requirement of the sensing range? If it is not feasible, I'll go back, increase the number of reserve stations, and repeat the step. So that's I solve this until I'll get a feasible range of the sensors. And once we get everything, the design is complete. All this design is an offline design for a given territory and speed ratio. So these are some examples of the solution. We consider one territory. If we have only one reserve station, the priority region and the monitoring regions are bigger. In general, if we increase the reserve station, the area shrinks. If we increase another and another, the area shrinks, but the reduction is not significant. After some time, the reduction in area is not significant. So it is a question of initial cost, initial reserve station cost, and the what is the saving in the sensor range. Yeah, and so for this problem, we consider the 3 as the optimal value, and we define the solution. So it looks like that. Here, these red circles denotes the critical points which are manually defined for an obtain monitoring region. The blue squares denotes the best location for the monitoring place there. It can be a best location. And then the blue circles will denotes the if my defender is equipped the best minimum sensor radius, how it works. Practically, sensor radius will come in some integer number, so we have some buffer there. Yeah. So now it defines all the design. So how you utilize it in the actual solution is just all offline. Now how you do online? We use the same concept. We define the cost for the doing the task from initial location to the first task. We take the distance when feasible. If it's not, we take in kappa. Then in subsequent, if it is like forward time feasible, we take the distance. If it is forward time infeasible, we take value kappa. If it is negative, we take infinity. All these concepts same. There's only change if the intruder is within my priority region. Even though it is forward time feasible, I can do it. I purpose task by keeping the value of kappa for subsequent task. So it avoids the assignment as subsequent task. So indirectly, it forces it to do it as a first task. The optimization problem is same. We solve this problem. The dream algorithm is also same. We solve the problem, calculate the Q number of assignments, add those many defenders in the team, solve the problem. So we'll get a minimum number of defenders required. So again, here we are adding some extra steps for the monitoring purpose. We'll check if all critical points are monitored or not. If not, we add extra defenders for monitoring purpose. And also, if we say if any unassigned defender is not required, we remove it from the team. Philosophy, it's very same as the dream. Just we need to find out the priority region to enforce it as a first task. Yeah. So here I'm saying first territory, then reserve stations. With the reserve station, we calculate the priority region omega p, then omega m, then the critical points on the boundary, and the best location for the defenders. Now, we have to see the intruder I and IF critically. If I comes here, the D2 is trying to go for I and IF is also assigned to D2. Now, I is trying to deviate the D2 from the IF. Once IF enter the priority region, it is assigned by D6. Reason is, if I is trying to deviate, D2 may not be able to go back and capture IF. So we have to give a guarantee that it should capture. We are adding extra defender whenever it the last moment when it was feasible for a reserve station. Now here we can see this D4 is moving such that it can maximize the sensing range and maximize the coverage. D1 will be removed as it is not required in some moment. Yeah. So here we are dynamically adding and removing the defenders from the team as required and giving a guarantee that all the intruders will be captured. Yeah. So what are the advantages of the P dream? So we can see earlier dream, the performance was degrading too much, and as the agility of the intruders are increasing, it was tending to 0%. At least one intruder was penetrating. But now we can get a success about 95, or for all cases where intruders are 6, 8, and 10, we are getting sufficiently high performance, a success rate. So next is a decentralized solution. So until now, we solve all the problem in a centralized way where defender lack as a team, they have no full information. So we'll define some sensing range problem. So here we are using the cost asCijf as the distance when it's feasible. The cost remains same. The changes happen in the formulation where I'm using Cij of mu I delta ij. So here the definition of delta ij is defender I will do task j or not. It's not in a subsequent way. In any way, if defender I executes a task j or not, delta ij will take value between 0 and 1 only. And the Cij of mu I is the accumulation of the cost for a path or for a trajectory mu I. Mu I contains the assigned task in a sequence and what is the total cost for executing entire trajectory. And here we are using the CBBA method, which is consensus-based bundle auction algorithm. And the CBBA works on the philosophy of bidding and consensus. First, every agent will bid for a path individually for one task each. Then they will go for the consensus. Lowest bidder will get the value. Now from updated location of the task, it will bid again for the next task. And this continues until all tasks are executed or until all tasks are assigned. And every step they will have a consensus. The CBBA is taken from paper by Choi and Howe from 2009. This is the distributed solution with which can handle the partial obscurity. It is online computable, but the solution obtained is suboptimal due to its auction method. This algorithm where its Cij is taken as the Li of Pi and Nj minus Lb. So it is like addition where to add extra agent, extra path, extra new task minus the cost of the previous task. This consensus. So now we compare these methods with the adaptive partitioning method published in IISc 2020, where they consider the problem of protecting a circular territory, where intruders are coming with some distributions. Here they actually sectorize the problem, and these sectors are dynamic. As sectors are dynamic, they define this solution as the adaptive partitioning, where partitions are adaptive in nature. So they estimate the arrival distribution of the all intruders, and then after sectorizing, each defender in each sector will be handling the intruders in that sector. And these are the success rates for uniform distribution, void merges, bimodal, and time varying. In all cases, the dream solution, a decentralized multitask STMT solution performs better. We here work on both approaches, as the earlier work considers defenders operating only on the perimeter. The first row denotes the delta omega, where the defender is restricted to operate only on the perimeter. And the second row says that defenders are allowed to operate inside the perimeter also. So here we can see the notion of distance. The distance is in notional sense, where you can take Euclidean distance or the line integral along the path or the line integral around the boundary. It doesn't make any difference. What are the kind of distance we change? It should be like homogeneous for all scenarios. Yeah. The application of the dream algorithm for pickup and just-in-time delivery in problems. So the first motivate. We just convert the problem into pickup and just-time. Defenders need to neutralize multiple intruders in a sequence. So normally it does that. It capture first intruder and go for the second. But what if every time you require some new ammunition, you have to go back on the reserve stations and take it? So the solution will be you have to go for do some tasks, go back, take extra resources, come and neutralize. So it is very similar to the pickup and delivery problem, where robots will go for a pickup location, load some items, then go for delivery and unload it at desired time. So if we define a task as unloading at desired time, we call it as a pickup and just-in-time delivery problem, where it functions of pickup location, the time of loading, delivery location, time of unloading, and the final time it should be delivered. So here we are defining the temporal constraints. So if robot will first pickup, then first delivery. Now first delivery is restricted to operate on a specific time. If we reach earlier, we have to wait. And for second delivery, if we reach late, we are failed. So we have to make sure that robots operate such that it will execute all tasks properly. And yeah, just-in-time philosophy is already used in automation and automobile industry, but all those problems are predefined. Once a single vehicle manufacturing is there, we know what parts needs to be automated in one sequence. Unless and until we are manufacturing a new vehicle, the process remains same. So the problem can be solved in offline function. But when you are using it for the warehouse, every time you order some new items, the pickup location may be different, and we need to have a solution which is online. And Dream can give an online solution because it requires only 2 steps. All earlier solutions was using a pruning and growing and pruning algorithm, where you solve the task assignment problem once, see if it is feasible. If not, add one extra agent, check it is feasible or not. Do it until you get a feasible solution. Here you don't require that. You can get in 2 steps. Yeah. So here the cost concept is very same. Here we are using the CIJF, the first task cost, the distance from the robot to the pickup location plus distance from pickup location to delivery location. Yeah. Here, notion of distance is not the Euclidean distance, but what are the distance we get from the map of the warehouse environment? What environment? It can be Euclidean, it can be Manhattan, it can have some any Dubin's curves, anything. Whatever the distance agent can obtain from the map with any algorithm, we can use that. And yes, the condition is like what are the minimum time required should be less than the time available. We take as the distance. If it is forward time infeasible, we take kappa toward that assignment. In subsequent, we follow the same step. From agent will move from the task A to task J. The distance is we are traveling from the previous delivery location to the next task pickup and delivery. It is like time is feasible, available required time is less than the available time. We take the distance as it is. If it is forward time infeasible, we take the distance kappa, and if it is a negative time, we take the infinity to avoid that assignments. Yeah, and the cost, the optimization problem is same, exactly with the changes in the cost function. This is a hardware experiment we did here in the lab. The timer is the real-time clock is placed here. The two robots are used R1 and R2. A task are go for pickup and then delivery. Pickup is denoted by pink color and the delivery is by blue. And the desired times are denoted here. So now robot 1 go for the first pickup, robot 2 will go for P2. Once robot reaches their desired location, it aligns towards the table this side to denote that it has executed the task. Just for the visualization purpose. So now after pickup 1, it is going for a D1. The robot 2 is going for delivery 2. So here at 35 seconds, delivery 1 is complete, and then robot moves for its next task as P3. The defender 2, so robot 2 is waiting here till the 50 seconds. Once the 50 seconds are required time, desired time is reached, it will move away and go for its next task. Yes. So now after doing the pickup 3, the robot will go for delivery, and this robot will go for the pickup at 4. So in this problem, the robots are already considering their turning radius and what are the distance available, and all those constraints on the trajectory planning are inherently considered while calculating the distance from the map. Yeah. So here D4 is already done, so it will wait there. Meanwhile, this defender will, this robot will go for the pickup 5 here and then deliver. It aligns means the pickup is over. Now it's going for delivery. And it get aligns before the desired time of 2 seconds. Yeah. Conclusions. In this work, I formulated the spatio-temporal multitask assignment problem, which facilitates the PDP to solve for a multi-agent, multi-capture solution. Earlier, all solutions were you are capturing 1 versus 1. Here it is first time we are proposing sequential capture for heterogeneous intruders. Then the dream algorithm provides non-iterative solution, which is a 2-step solution, and it can be used for solving any online problem which consists of spatio-temporal requirements. PDream provides a offline solution and then provides a multi-capture solution for agile intruders. Then decentralized solution is the first solution which can solve, which can handle the partiality observability and gives a feasible solution. And yes, the already existing just-in-time approach has been exploited for the real-time problems where tasks are unknown and tasks are online, and we can solve it using dream approach. Yeah. Future direction goes in 2 ways. One is in PDP, where we can increase the complexity of PDP. We can add some non-holomorphic constraints on defenders. Defenders can have angular constraints. We can go for the problem can be extended to 3D PDP, where we are defining the 3D boundary over around a territory. Here, it is not only that having a Euclidean distance in a 3D space, but we need to consider the extra cost required for climbing up and climbing down. And then width of perimeter, all work, he considers that, okay, there's a boundary and there is a unique point where you can capture. But if it is a boundary which is like a layer, you can capture the intruder in any point between the layer that can be extended. Yes. And the theoretical questions on the what if we have limited resources? We are given tasks. We assume, okay, what is the extra defenders, extra resources required? If I have those many, it is okay. I can do tasks. But what if resources are limited? The question comes, which task to be done? Or can I alter a little bit in a task temporally so that all tasks can be done? How to alter those tasks temporally? Publications. So first is the work, is the decentralized work is published in TRO. The next is dream work is published in transaction in AES. The third is the PDream work is submitted to SMC systems. It is revised and it is under review. The fourth is like warehouse work where we are using the pickup and just-in-time delivery is submitted to RIS. It is under review. Yeah, and the last is music problem. This is a fun experiment we did in lab last summer. So I'll just So whenever a human plays piano, we have fingers, and they need to be placed at different location at different time. If we do it on properly, we can listen to proper music. What if instead of fingers, we use robots? Robot needs to go that specific location to play that specific note at specific time. Yeah. And this video, hope you enjoy this happy birthday music. This is played at 10x speed because the turtle words are very slow to catch up the actual. It is played at higher speed. These are the key references used in the work. Any questions?
Any questions?
Actually, a nice work presentation. Is you said that the speed of the defenders is assumed to be that of the intruders.
Yes.
So
We are assuming the number of intruders are more. So to match up that, we should give some speed advantage to defender.
sure. But maybe it's more relevant for the future work. But what happens if the speed is actually smaller than that of an attacker, because you can possibly know its position beforehand, right?
Yes.
And it is always good. It is a threat only if it enters a region which is bounded. So sometimes you may not need speed advantage because you know where it's coming from. You can detect it and reach to the perimeter or something.
Yes. So in that case, you may require more number of defenders. As your lower speed, the sequential capture may be difficult. And then problem converts it to you have more number of defenders to handle lower number of intruders.
The other question is, so you said that non-holonomic constraints is something because. So in what way do you think the results can be affected if there are turn rate constraints for the defenders? Any thoughts on that or?
Okay. Practical is like, if you ask me, is like, it's not a technical answer, but I would like to solve this problem very non-technical way by adding some extra time to handle the end capture scenarios. So if I put some buffer time extra to handle that part and work on only Euclidean distance and move forward, it may be more efficient to get a practical solution. But if you want to get final solutions, yes, you need to consider the Apollonius circle where you have a capturing range, then calculate the worst case scenario to what is the worst case distance in Apollonius way where in a closed environment you require. And that worst case distance may be different for each scenario. So for what I said first is like consider the worst of worst and get solve it.
Thank you.
Yeah, in all these simulations, we have shown that defenders are not intelligent. I mean, intruders are not intelligent. They are not cooperating. Right? What if they cooperate?
If they are cooperating, yes, then problem becomes difficult because then lower number of defenders may not be suffice to capture all. Because as I say, showed one scenario where they are initially coming at two different locations close by. So I'll go there. So this scenario. Initially, I1 and I2 are coming at two locations, but then after some time they try to deviate. So this is not exactly, we are not assuming they are cooperating, but something kind of this will happen. So if we are using the P-dream where we are prioritizing, P-dream consider the extreme scenarios where intruder can take any action. So that any action can be one of the optimal action from the cooperative way. So P-dream can handle it.
So here you have shown that the intruder doesn't sense anything too, right? So if that comes into picture, how does the problem changes to, or what do you think that we need to address to take care of?
Okay, so if intruder is intelligent and is so we can consider some trivial scenario where intruder comes and goes approximately tangentially to the boundary, and then the capture happens only at the infinite time. So then to make a problem real world, we need to define some time limit before which if intruder doesn't penetrate, we stop the game or we stop the problem. At least we need to consider some limited energy by the intruders. Otherwise, intruder can just take a circular region, operate circularly on all one circular territory, and this goes on infinitely. So we need to assume some energy limit of the intruder.
Just to clarify, all of these solutions are that intruder is gonna come to the perimeter, and once it comes very close to the perimeter, that's when the defender actually attacks the intruder.
Yes.
So my question is, what about the prospect of the defender? Once it detects the intruder, it doesn't wait till the intruder comes to the perimeter, but actually goes out of the perimeter by itself and then tries to neutralize it. The reason why I thought of this is because let's say the intruder was able to overcome the defender. In that situation, then a backup defender can then be prepared.
So what you're asking is a guarding problem where defenders are allowed to go outside. So let us consider you are trying to protect some international waters and the ocean waters, which are owned by some country. If something is on international waters, you can't do anything. It's like they're allowed to be there. If they only enters your region, then only you have a right to neutralize. But also for the land boundaries and everything. So problem is limited where you don't have any authority outside your boundary or outside your perimeter, you are not authorized.
But in that scenario, let's say the intruder is able to successfully neutralize the defender. Wouldn't that be a problem, like waiting until the attacker is coming all the way till the perimeter? Because if it neutralizes, then it's already in the perimeter.
Yes, but this structure of the problem says that you are not authorized to go out.
Well, this question is interesting. What if intruder is trying to neutralize you? Here we are assuming defender can neutralize the intruder. Intruder doesn't do anything. What if the other way around comes into picture? How do you?
Okay, so in that scenario, we may need to have a buffer layers. So we need to have a layer defense. The outermost layer where you first, if you failed in outermost layer, you have an immediate layer where you try to penetrate or capture it. But yes, it is having the neutralization ability of the intruder. We may need to send more defenders there to get some advantage.
Any questions from Professor Mangal? Do you have any questions?
So nice presentation. So I have two questions or maybe question query. So you have not commented on the distributions of the defender. Will that be at center, whether they will be on the perimeters? Could you tell something about that?
So initially, at the initial location, defenders are assumed to be at sparse on the perimeter. But as the problem goes on, they can be closer. But then if they're going one side, one of the other region will not have any defender to monitor that region. So one of the defender from research station will be sent there to make sure that you're monitoring the entire region.
So do you
So
have assumptions? Because if perimeters, so it will be evenly covered for all perimeters, or how are they distributed?
Question is the perimeters are evenly monitored or the monitoring distributions are uneven?
is monitoring is like if any defender monitors this monitoring is done. If you monitor for if some more intruders are closer in one region, you may require more defenders there, so you can monitor that region multiple times. But it's like monitor. It's just like you monitor or not. Doesn't matter
So
you're monitoring it by one defender or multiple defenders.
you
But
do
you
not
should monitor it at least one.
Sridhar, you don't know a priori this, right? If you know the a priori, the question is, so that's why the question is that here I believe you do not know a priori, right, intruder?
1 minute. Can you one just one?
Do you know how intruder is going to come a priori?
So we don't know how the intruder is coming a priori, but we are estimating its arrival location and arrival time.
But how? If you don't know, how are you estimating?
How are you estimating the arrival location and this? Because you don't have the prior information, right?
Yeah. So for non-monitoring scenario, we are just using the straight line linear. We are linearizing its previous points, and for non-monitoring, so for maneuvering, we are using a spine. We are just linearizing and predicting it. Even though our predictions are wrong, we are resolving the problem at each step, so it becomes better and better.
I think we should look into this. Okay.
Okay.
It may not be sound way of me. Second, you have not commented on the speed. See, your presentation, you might like or may like to comment on the speed. So, the defender has a faster speed or lower speed or equal speed problem?
Defenders will have higher speed.
Okay. Okay, then it has a speed advantage, right?
Yes.
Okay. And when you talk about maneuverability, so you are considering it's holonomic, right? It's
Yes.
not non-holonomic, right?
Okay. So defenders here needs to go and pause, wait. So it is more kind of a quadcopter scenario where you can need to be hover till the intruder comes there. So in that scenario, we don't require to consider the holonomic constraint much. It is questionable when we are considering the fixed wing aircrafts, where you need to consider.
No, I am asking when you consider maneuverable case, as you have considered, does it has to do anything with the holonomic or non-holonomic? Maneuverable case would be holonomic or it would be non-holonomic?
Maneuverable.
Maneuverability is holonomic. Intruders are holonomic.
That's okay. Okay. And how do you assign? What is the criteria of assignment? Apart
So
from the method, so that you take a time measure, right? That is a Euclidean distance because you have considered. So anything else? You have any priority or resource allocation?
yes. So once we get the solution, the feasible solution at the end of dream or p-dream, we get the sequence in which the defender is assigned for the intruder or the spatio-temporal task. So it will follow that the spatio-temporal sequence and neutralize all intruders.
So the way you have formulated the problem to summation so that you solve it sequentially, isn't it?
It will give the assignment of delta IJF and delta KJS. So if it is assigned, then defender will follow that path.
Okay, so have you commented anything about endurance? Because you are talking
No.
about that endurance and the area what you are going to cover. Have you commented anything on the endurance? Because I know you are solving the perimeter defense problem, but physical vehicle has some endurance limitation, right?
Yes. Endurance is not considered.
Oh, okay, thank you.
So endurance is not considered, but its influence can be like, we can limit it can be solved in decentralized formulation directly by making sure that your assignment, your distance, the cost of the trajectory for all the path mu I, if should not be more than some endurance value. The distance should be maximum distance can be limited for each path.
Okay, thank you very much.
Thank you. Any questions from online audience?
No further questions. Like to thank everyone. Very good presentation. To close the discussion as well, I request all of you to be online also, except the examiner. Can I request others to sign off, please?